right? So the first thing we did is we talked about the fact that gases have many different units. So quick refresher here, and I will give you the conversion on the third test. So gases can be measured in atmospheres. They can be measured in millimeters of mercury. Remember that in honor of Torricelli, they renamed a millimeter of mercury a torr, so those two are synonymous. If slash when you take physics, you'll learn that physicists have a different pressure unit, called the Pascal, that they are just absolutely crazy about. So there's your conversion between pascals and atmospheres. There's 101,325 Pascal in an atmosphere. So if you, excuse me, if you need that conversion. Boyle's Law. Let's talk about Boyle's Law. So Boyle's Law is the first of our simple gas laws. There's going to be 4 simple gas laws. We got 3 of them on Wednesday. Boyle's Law is the first. Yes, you do have to memorize these formulas for all these simple gas laws. Boyle's Law is really the one that looks a little different because pressure and volume are inversely proportional. The law we end up with is this one, P1V1 equals P2V2. So the initial pressure times the initial volume equals the new pressure times the new volume. So that's that guy. It doesn't matter what unit your pressures are in and what unit your volumes are in, as long as they're both the same. So if I'm plugging atmospheres in on this side, for my other pressure, I need to be plugging atmospheres in as well. If I'm plugging milliliters in here, I need to be plugging milliliters in here as well. That doesn't matter as long as they are the same. Then we got Charles's law that says volume and temperature for a non-rigid container, so something that can expand and contract like a balloon, volume and temperature are directly proportional. And when the variables are directly proportional, we get a proportionality. This is where people like to cross multiply the two variables, right? Anytime in this gas law unit that we have a temperature, that temperature has to be in Kelvin. So remember, how do we go from Celsius to Kelvin? We take that Celsius temp and we add 273.15 to it, and that's how you get it into Kelvin. But conversely, if you have a temperature in Kelvin, you want to turn it back into Celsius, you would subtract the 273.15. Alrighty. And then we got the old combined. Oh, I'm sorry. Actually, before we get to the combined gas law, we had Gay-Lussac's law. That's where we left off. So Gay-Lussac's law was our relationship between pressure and temperature for a rigid container. So for Charles's law, the volume can change, but in Gay-Lussac's law, the volume is fixed. So with Gay-Lussac's law, it looks just like Charles's law, but instead of volume, we have pressure. So it's P1 over T1 equals P2 over T2. And again, you can cross multiply. And again, temperatures have to be in Kelvin. So I thought a good way to review here to get going would be to practice these 3 gas laws that we got on Wednesday. So I'm going to throw 3 problems up here, and I want you to try and do them, and then we'll go over them, okay? And I'm going to mix them up, okay? I'm going to mix them up for you, all right? So here's number 1. Yeah, I'll just give you 2 of them because that's all I probably got room for. I'll give you 2 of the 3 gas laws. Give it a shot, folks. What temperature is needed to increase the volume of a gas from 0.750 liters at 25 degrees Celsius up to 2.5 liters? And a balloon at 1.05 atmospheres contains 3.15 liters of gas. What will be the volume of the gas if the pressure increases to 1,350 torr? So we got Boyle's law, we got Charles's law, we got Gay-Lussac's law. You're going to need to use two of those three. Give it a shot. You got this. All right. This top one's got temperatures and volumes. That's Charles's law, folks. V1 over T1 equals V2 over T2. We got two volumes. So here's our initial volume, 0.750 liters. And our new volume, this thing is expanding to 2.50 liters. So we must be heating it up. We got an initial temperature here. So that's T1, but it's in Celsius. We got to add 273 to that. That's 298 Kelvin. And we're solving for T2. A lot of people like to cross multiply here. So here we go. 2.5 times 298. That's 745 liters times Kelvin equals 0.750 liters times T2. Divide both sides by 0.750 liters. Liters cancels out. We're left with a new temp in Kelvin, 745 divided by 0.75. That is 993 Kelvin. If you wanted to turn that back into Celsius, you would subtract 273, and that'd be 720 degrees Celsius. So you got to heat that sucker up hot. You're going from 25 degrees Celsius all the way up to 720 degrees Celsius. That is hot, 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 hot. Yeah, I don't know. You throwing that? There must be some kind of special balloon. You're chucking it in like a fire or something. So there we go. All right. Any questions on the top one? Well, all right. I'm going to convert. So here's the problem, right? If we pull the information out, we have a P1, we have a V1, we have a P2, and we're looking for V2. But the problem is our P2 and P1 units of pressure are not the same. Now, I'm going to convert P2 into atmospheres. There's 760 millimeters of mercury or torr in an atmosphere. But you could convert atmospheres into torr. That's totally fine as well. 1,350 divided by 760. That's 1.78 atmospheres. So here's really the problem that we have. We're going to set up Boyle's law. P1 V1 equals P2 V2. And we're solving for V2. Now, you could do the algebra up front if you like. V2 equals P1 times V1 over P2. Totally up to you. Doesn't matter to me. 1.05 atmospheres times 3.15 liters over 1.78 atmospheres. Atmospheres is gone. Left with liters. 1.05 times 3.15 divided by 1.78. That's 1.86 liters. 1.86 liters. So this should not be shocking, right? Boyle's law says pressure and volume are inversely proportional. If the pressure increases, then the volume should decrease, and it does. Goes from 3.15 down to 1.86. Essentially, you're smashing it down. So, of course, it's going to shrink. So at this point, we have three simple gas laws. And somebody got the bright idea to combine them and make one big old, at the time, crazy gas law called the combined gas law. So here's the combined gas law. The combined gas law takes Boyle's law, Charles's law, and Gay-Lussac's law and combines it. And you end up with P1 V1 over T1 equals P2 V2 over T2. And now what you can do is you can simultaneously change pressures, volumes, and temperatures. You can, as long as you know 5 out of 6 of these variables, you can solve for the sixth. You don't have to hold a volume, a pressure, or a temperature constant. You can change all 3 of them and still be able to predict that sixth thing. So it gets a little messy. This is one where I don't like to do the algebra up front, but you totally could. Like you could multiply by T2 and T1 and then whatever you got to do. I plug it and chug it and then go from there, but you're going to have to find what works for you. So let's take a look at a combined. So hopefully you can see, first of all, that it's got all 3 gas laws in it, right? Cover up temperature, boil. Cover up pressure, you got Charles. Cover up volume, you got Gay-Lussac. Now there is going to be a 4th simple gas law called Avogadro's law. Okay, they thought they were done. When they combined these gas laws, they thought this was it. And then Amadeo Avogadro came along and said, I got one more for you. And unfortunately, they had already used the term combined gas law. So we'll talk about that in a minute. But first, let's work a combined gas law problem. So if nitrogen gas occupies 1.50 liters at 0.985 atmospheres and 19 degrees Celsius, what would be the pressure for a sample of nitrogen gas that occupies 4.35 liters at 25 degrees Celsius? So that same sample of nitrogen gas, what would be its new pressure? So the first thing I like to do, I like to pull the information out of that problem. So I'm going to write this down. We got B1 equals 1.50 liters. What else we got in there? We got P1 equals 0.985 atmospheres. And we got T1, that's 19 plus 273. 19 plus 273. Remember, you got to put it in Kelvin. I just do it right away so I don't forget. That's 292 Kelvin. Then what else we got? What would be the new pressure? P2 is what we're solving for. We got a V2. V2 is 4.35 liters. And we got T2, that's 25 degrees Celsius, which is 298 Kelvin. Oh, yeah, I'm going to make myself a note. We need to talk about what standard temperature pressure is. Put that down there. So I'm going to hop out here for a second. I want you to try to solve for this. See how the algebra goes. You got to find a way that works for you to get P2. Okay, so I'm going to let you try it, then I'll go over it. And, you know, if you made a mistake, hopefully you see what happened. So you got this. Hopefully that was enough time. I'm going to start working this problem here. And you can kind of follow along and see how it went. So I'm going to plug everything in and then try to solve for P2. So I'll multiply by T. Well, I'll show you. Here we go. So I'm going to get a number here and I'm going to get a number here. So I simply multiplied these two and divided by that. I took 4.35 divided by 298, and I ended up with that times P2. And now I'm going to divide both sides by 0.0146 liters per Kelvin. You can see the liters canceling out, the Kelvin canceling out, and being left with atmospheres, which is good because we're looking for a pressure. .347 atmospheres. So if you took this same sample of gas, if this nitrogen gas occupies 1.5 liters at 292 Kelvin and 0.985 atmospheres, if you increase the temperature slightly and expanded it, the pressure would drop from 0.985 down to 0.347 atmospheres. I made myself a note here for STP. So first of all, any questions on that? How did that go? Did we get 0.347? Maybe you solved it differently from me, right? Maybe you cross multiplied from the beginning or something, right? I don't even, there's so many ways you could tackle this problem, right? You could have multiplied by T2 divided by V2. You could have said P2 is P1 V1 times T2 over T1 times V2. I mean, you could have done a whole bunch. How many people got 0.347 ATM on that one? Nobody. One person. Kristen, way
Yeah,
to
I got 0.343, but I think
That's just
I added
rounding. That's just rounding,
0.35
Elliot.
to the Kelvin.
Yeah, I think that's fine. That's probably just a
Okay,
rounding. I would take that on a test. Yeah.
cool.
Cool. Awesome, guys. Well done. Okay. STP, before I forget, not Stone Temple Pilots. No, no, no. All right. STP stands for Standard Temperature and Pressure. So standard pressure is 1 atmosphere, and standard temperature is 0 degrees Celsius, which of course you're beginning to learn. You can't use Celsius when we do math. So we may as well put that in Kelvin. That's 273.15 Kelvin. If you are told that a gas is at STP, they are giving you two variables. They are telling you that the pressure is 1 atm, and they're telling you the temperature is 0 degrees Celsius or 273.15 Kelvin. So I like, when I hear STP, I think of a freezing cold day at the beach, right? Because if you're at the beach, you're at sea level, that's 1 atmosphere, and 273.15 is freezing outside, right? So 0 degrees Celsius. Okay, cool. So STP, I think on the first homework for the gas laws, they tell you the gas is at STP. So make sure that, on a test, I could say STP. Make sure you know that STP means 1 ATM, 273.15 Kelvin. Awesome. So the simple gas laws, they thought they were done after Gay-Lussac's, and they combined Boyle's, Charles, and Gay-Lussac's law into one combined gas law, and boy, the chemists thought they were done. And then our old friend Amadeo Avogadro came along and said, but wait, I have one more for you. Now, this one seems like the most common sense of all gas laws. It's the simplest it's the simplest gas law conceptually, but the most difficult mathematically. I know. Here's what Amadeo Avogadro said. Amadeo Avogadro said, if you have a container that can change its volume, so like a balloon, a non-rigid container, then the volume of the of the system is going to be directly proportional to the amount of gas. And this, of course, is common sense. If we take a balloon and put more gas in there, it's going to get bigger. And if we take a same balloon and we let some gas out, it's going to get smaller. The amount of gas and the volume are directly proportional. So since they are directly proportional, we're going to get another equation that looks just like Charles's and Gay-Lussac's. When the variables are directly proportional, you end up with that fraction, that proportionality. Our abbreviation for the mole is an N. So here's Avogadro's gas law. Avogadro's gas law says the amount of the gas initially divided by its volume will be equal to the new amount of the gas divided by the new volume. That's Avogadro's law. So yeah, N1 over V1 equals N2 over V2. So this gas law should hopefully be common sense, right? But here's the problem. The problem, of course, is that whenever moles are involved, that means stoichiometry. I want you to go ahead and read this, and I'm going to pull the information out of it and write it on the board back here. And we're going to talk about how this problem is certainly not straightforward. Uh-oh, somebody just got booted. They'll be back. Oh, I knew it. Ah, it was Kristen. All righty. All right, we got a volume that is 2 liters. V1, 2.00 liters. Temperature, so we're at constant pressure, constant temperature. Pressure and temperature are changing. We've got an amount of the gas. The initial amount of the gas is 0.750 moles. A light is shined, shoned. I don't know which word is the right word, so we're gonna put a light on the balloon, and all the O2 is converted into ozone. What is the new volume of the gas? And of course, if you're paying attention, we got a problem. If we're going to use Avogadro's law, N1 over V1 equals N2 over V2, if you got 4 variables, you got to know 3 of them. And the problem is we got N1, we got V1, we're looking for V2. I need N2 before I can solve for V2. And the issue now is that I don't have to give you N2 because I described this. This is a chemical reaction, and you're going to have to do a bunch of things here. You're going to have to write a balanced chemical equation. Then you're going to have to do some reaction stoic, and then you're going to have to do the problem. Let's go back and look at what was stated. We got this balloon that's full of oxygen gas. I'm going to draw the picture. We got a bunch of oxygen gas in here. Then we are going to shine a light on the balloon, and that ultraviolet light is going to turn all the oxygen into ozone. And I want to know what's going to happen to the volume. So what just happened here is a chemical reaction. O2 is getting turned into O3. And before we can do anything with a chemical reaction, we need to balance it. So we need to put a 3 here and a 2 here. And now it's reaction stoic time. 0.750 moles of O2. I want to know if all of that is converted into O3, how many moles of O3 are there? Once you give me N2, then it's a piece of cake. So I want you to go ahead and do this reaction. Stoic, get N2, and then once you know N2, I don't care if you cross multiply it, whatever you want to do, go ahead and solve for V2. You got this, folks. So it's a 2 to 3 mole ratio. That's 0.500 moles of O3. That is my N2. Now I know everything. I know 3 out of 4 of the things, and I can solve for the 4th variable in my Avogadro's law problem. Here we go. .33 liters is what you should get. If you took this balloon and you took all of the O2, so you had a bunch of O2s floating around, and you had shined the light on it, and all the O2s got turned into O3s, there would now be less gaseous molecules floating around in there, and the balloon would shrink. And you would go from 2 liters of volume down to 1.33 liters of volume, because for every 3 O2s that go in, only 2 O3s come out. You're effectively reducing the number of gaseous particles in there. Yeah. So Avogadro's law, common sense, right? Okay, more gas in a non-rigid container, bigger it's going to be. Less gas in a non-rigid container, smaller it's going to be. Common sense, right? But because of the mole, you got to do stoic, and people freak out when they get to that.